Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X, published on November 20th, 2025, about 3 days ago. It introduces Nemotron Elastic, a many-in-one training framework that carves out nested reasoning models that match or beat state-of-the-art accuracy, while cutting family training costs by over 360 times and using only 110 billion tokens. The paper is titled Nemotron Elastic, Towards Efficient Many-in-One Reasoning LLMs. And as we will see later, the implications for how we train and deploy whole model families are pretty significant. So after that overview, Figure 1 puts numbers on the promise of Nemotron Elastic. The left panel shows that the nested 6, 9, and 12 billion parameter variants all reach strong average reasoning accuracy, matching or beating other 8 to 12 billion parameter baselines, even when used zero-shot. The right panel compares scaling costs, and it shows that token usage and deployment memory remain almost flat as more elastic submodels are added, whereas the traditional Minitron series grows roughly linearly with family size. Alright, Figure 2 explains how Nemotron Elastic actually trains and deploys its many-in-one models. The left side shows a teacher and a student network, where a router reads the chosen budget, like 6, 9, or 12 billion, and applies differentiable masks to the student. Knowledge distillation transfers behavior from the frozen teacher into all these masked variants. On the right, deployment simply slices out the 12, 9, or 6 billion subnetworks from one shared checkpoint, so no extra fine-tuning is needed. So while Figure 2 showed the training pipeline, Table 2 quantifies the token savings from that design. The table compares 3 methods for producing 6 and 9 billion parameter models. Traditional Nano V2 compression with the Minitron SSM approach spends about 480 billion tokens on exploratory runs, plus 270 billion on final training, for roughly 750 billion in total. Nemotron Elastic skips exploration and finishes in only 110 billion tokens, which is around 7 times more efficient. So while Table 2 highlighted token savings, Table 1 shows that accuracy really holds up. The Nemotron Elastic 12 billion model slightly beats the Nano V2 12 billion baseline on average reasoning score, about 77 versus 77. The 6 and 9 billion Elastic models also track closely to the larger Nano V2 checks, staying within a few points. This means the single many-in-one training run preserves strong reasoning quality across all deployed sizes. Well, Table 3 drives home the deployment advantage of the many-in-one design. The table compares memory for storing multiple checkpoints in BF16 weights. Nemotron Elastic holds 6, 9, and 12 billion parameter models in just 24 gigabytes, while Nano V2 needs 42 gigabytes for only 9 and 12 billion. That means the Elastic setup stores more models, yet still cuts deployment memory by roughly 43%. So while Table 3 contrasted deployment memory, Table 5 examines how different budget sampling schemes during training affect accuracy. Table 5 compares uniform sampling to adjusted non-uniform sampling across 6, 9, and 12 billion Elastic models on Math 500, AIME 2025, and GPQA. The adjusted scheme slightly changes scores for the 6 and 9 billion models, but it clearly boosts the 12 billion variant, especially on AIME and GPQA, where accuracy rises by several percentage points. So while Table 5 focused on sampling strategies, Table 4 breaks down how the two-stage curriculum boosts accuracy. Stage 2, which adds extended context training, improves performance for every model size and benchmark. The 6 billion model gains the most on AIME 2025, jumping about 20% relative. Even the 12 billion model still picks up a few extra points, which shows that long context reasoning practice is crucial for competitive scores. Alright. The big message is that Nemotron Elastic turns one hybrid Mamba-Attention model into a whole nested family, keeping strong reasoning quality while slashing training cost by hundreds of times and cutting deployment memory almost in half. That makes sophisticated multi-scale reasoning models far more practical to train and ship. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.